So now that we've talked a bit about partitioning and splitting with parallel streams internals, let's turn our attention to the processing phase. Remember, so it's basically split, apply, combine. So apply is the processing part. That's where we're actually doing something interesting to the chunks that we've split up with the split phase or the partitioning phase. And what we're going to do here is we're going to talk about how parallel streams will process these chunks that are created by the parallel spliterators in parallel using the common ForkJoin Pool, which is this super cool framework that you can learn more about at the link at the bottom of the slide or by watching the rest of the video. So here, chunks, as I mentioned, are processed in the common ForkJoin Pool. This is a link you can read about the common ForkJoin, or actually you can read about the ForkJoin Pool in Java, and we'll talk about the common ForkJoin Pool in a second. But the ForkJoin Pool is a very interesting abstraction for pooling processors intended to optimize the performance in multi-core platforms by being able to basically fully throttle the cores to run as fast as they can and keep them busy with things to do. Now, I mentioned this very briefly early in the intro to the course, but I'm sure you forgot it because we haven't talked about it much since that point. What is a ForkJoin pool? It's a way to provide high performance, fine-grained task execution using data parallelism in Java. And data parallelism just means that you're using the data as the unit of parallel processing. So as you'll see in a second, you take a big chunk of data, a source of data, and you chop it up into little chunks, and then you process those chunks in parallel in a very fine-grained way. Like, each element in an array list is running in a separate, on a separate thread and on a separate core. Pooled, of course. The ForkJoin pool, and in general, and specifically the common ForkJoin pool, provides the parallel computing engine for a bunch of other higher-level parallel processing frameworks in Java and elsewhere. So the parallel streams framework, which we're talking about now, uses the ForkJoin pool, the common ForkJoin pool. The completable futures framework, which we'll talk about in the future, uses either the common ForkJoin pool or some custom ForkJoin pool if you decide to do that. And again, you can listen to an interview with the author of the ForkJoin pool, Doug Lee, who's a friend of mine and a colleague since the mid-'80s, really smart guy, great guy. He talks about how he implemented it, and it's really, really, really cool. So without getting too far off track, there's a framework for doing task execution in Java called the Executor framework. If you come back in the spring, you can learn all about the Executor framework because we'll cover that. In fact, if you come back in the spring, you'll get more practice with the ForkJoin pool. We're not going to cover it a whole lot in this course, but in the spring, we'll cover it more. And the ForkJoin pool is an implementation of the Executor service interface. And don't have to worry too much about what that means other than the fact that there's a bunch of different ways to have pools of threads in Java, and ForkJoin pool is one of them. And a ForkJoin pool executes things called ForkJoin Tasks, which are pretty interesting. We're going to talk about them. A ForkJoin task is an object that associates a chunk of data, could be a big chunk or small chunk or something in between, along with some computation on that data in order to be able to enable this fine-grained parallelism. And you can read more about data parallelism in Java if you read the link at the bottom of the slide, but that's basically the engine, the thing that does the actual processing is this thing called a ForkJoin task. And a ForkJoin task is similar, though not identical and intentionally lighter weight, than a traditional Java thread. And there's a couple of different threads in forthcoming Java. In traditional Java, in the Java that we know and love, there's one kind of thread called Java thread, which has certain properties. It has things like its own runtime stack, it has its own registers, it's got its own thread local storage, et cetera, et cetera, et cetera. That's what a traditional Java thread looks like, and it's pretty big and beefy and strong. Just a quick side note, with newer versions of Java that are not yet released in the standard Java but are available in early access form, they've now renamed these things as platform threads, and they are distinct from something called virtual threads. And that distinction will be more meaningful in a minute once I explain what a ForkJoin task is. So a ForkJoin task is kind of like the scrawny, little brother of the thread. And in particular, it doesn't have a runtime stack. It doesn't have its own registers. It doesn't have its own thread local storage. So it is, much more slimmed down. It's like a thread on a diet, basically. And as a consequence, you can have a very, very, very large number of ForkJoin tasks. You can have hundreds of thousands of them, millions of them, in fact. And they can run by being multiplexed atop a much, much smaller number of classic Java threads. So you might have, let's say you have n cores where n is 4 or 6 or 8 or whatever. You can have a number of threads that are worker threads, real Java threads that are mapped to those cores or multiplexed over those cores. And then you can have millions or hundreds of thousands of ForkJoin tasks, which are much lighter weight. And that's by design. The whole point there is to try to keep things lightweight so you can have lots of them. With modern Java down the road, what's called early access Java or Project Loom Java, they have these new things called virtual threads, which basically run on top of ForkJoin tasks and can be used to give you a threading feel without the cost of traditional heavyweight so-called platform thread. So armed with a little bit of knowledge of what the ForkJoin pool is, parallel streams are basically a user-friendly facade around the ForkJoin pool. What the heck do I mean by that? Well, ForkJoin pool traditionally has required object-oriented programming where you inherit from certain classes and you override certain methods, and you have to be careful about making sure you do things in the right way, and it's kind of a white box framework, which means you have to know the design a bit. So it's a little bit tedious to program, although it's very optimized and very scalable and so on. So what parallel streams basically do is they take that engine, the thing that I show on the right, and they wrap a functional programming facade around it, so you can do functional programming, but then take advantage of the underlying ForkJoin pool or common ForkJoin pool, as the case may be here. So you can think of streams as just basically a way to make parallel programming easier while still accessing all the powerful parallel engine features of the ForkJoin pool. Now, you can, in fact, program directly to the ForkJoin pool API if you so choose. It's still there if you still want to use it, but it is painful. And we'll not really talk much about that in this class, but if you come back in the spring, you'll learn more about that. Anybody here who's seen Lord of the Rings, one of the classic scenes is when Gandalf and Saruman are facing off in the Orthanc, like the room, the main wizard room in Orthanc Tower, and Saruman says, I'm paraphrasing, "I gave you the chance of programming Java streams willingly, but you have elected the way of pain because you chose to use the common ForkJoin pool instead." So don't be like Gandalf, right? Don't elect the way of pain. Make a better choice. And if you really, really want to see how to program with ForkJoin pool, there's a cool example here that shows how to do it using the complete works of Shakespeare, of course. What else? The ForkJoin pool is best suited for parallel programs that don't quite match the parallel streams model. And remember, the thing about the parallel streams model, the heart of it is taking data sources you can split evenly and efficiently using a divide and conquer like approach. When you can do that, parallel streams is your cup of tea. It's the cat's meow. It's the bee's knees, as they say. However, if you don't have that type of a design, then it's not quite the right thing to do. So you don't want to use the square peg in a round hole kind of thing. And here's a simple example that you can read more about at this link here. They got the source code in this example here. This is basically a program that counts the occurrence of a word in a recursively structured document hierarchy full of folders and files and subfolders and so on. So the thing to note there is that in this particular case, breaking things up into chunks is not easy because you've got variable size stuff, and each folder might have lots of files and lots of subfolders, or a few files, a few subfolders. So the parallel streams approach may not be the best approach. So here's a nice illustration of how to do this using the ForkJoin Pool framework. So what we're going to do here is we're going to create a linked list of things called Recursive Tasks, which is a linked list. We're actually using a linked list here because we're not worried about dividing this in half because we're not using parallel streams. And then we say for every folder, for every subfolder in a given folder, remember this whole thing is recursive, we're going to go ahead and create a bunch of new tasks called folder search tasks, which are going to look for a given word in that subfolder. And then we're going to go ahead and add that task to the list of tasks, and then we fork. And fork basically just arranges to run that particular task in a background thread that's part of the ForkJoin pool that's being used here. So for each folder, we're going to do this recursive splitting. And then for each document at a given folder, we're going to do the same thing. We're going to create a document search task looking for the word. We add that to our list of forks, our list of recursive tasks. We fork that so we can go ahead and arrange to run that concurrently or in parallel in a thread in the common ForkJoin pool. And then the last thing we do is after all this stuff, all these things then start to run in parallel. All that stuff gets run and is recursion, blah, blah, blah. And then at this given level, we have another loop that says, for every one of these tasks in the forks list, which we created here and now have spinning around running concurrently, wait for each of those subtasks to finish and then increment the count of how many documents they found that contained the word. And when we're all done, we return the count. So again, not that hard, but you can see there's a lot of stuff going on. You got to fork and you got to join and you got to keep track of things. So clearly you'd like something a little simpler, and that's what the parallel streams framework allows you to do. All the parallel streams that are in a process, in one process, no matter how many there are, will all share the common ForkJoin pool. So there can only be one common ForkJoin pool, and the whole purpose of this is to reuse it. And why do we do this? Because we want to be able to optimize resource utilization by having one place in the program that keeps track of what cores are being used globally within a process. And the reason for that is that way there's one place that we can keep track of all this stuff, and most importantly, we can do what's called the work stealing algorithm in order to make sure that all the cores are kept humming along as efficiently and optimally as possible. And we'll show more about that in a second. So it's kind of like Cerebro for Professor X, right? He has one place he goes in his mansion where he can keep track of the entire, planet, or maybe beyond, of people's thoughts, if you ever watched the X-Men. This is a very common pattern. This global versus local resource management trade-off is very common in computing. A good example of that, for instance, would be in Java, you've got a heap. You have one global heap that's used to allocate memory, rather than having, little pools of memory that you stick off to the side and kind of manage yourself locally. You have one global heap. And again, the idea is to make sure that you can have optimized memory management done by someone who's really clever to write the garbage collector, rather than each programmer having to figure out how to do it themselves. There's other examples, of course, in business. Universities, for example, sometimes have a centralized resource allocation model where all the money from tuition and grants and donations goes to the provost's office or the chancellor's office, and they decide who gets what. That's one approach. Another approach is basically called each tub on its own bottom, where each school or college keeps its own profit and loss, and then they pay a tax to the central group. So they're just different ways to organize things. When I first came to Vanderbilt, we had an each tub on its own bottom model for the schools and colleges. Then we went to a model that was a centralized model. Now we're back to an each tub on its own bottom model. And there are pros and cons, of course, with each one. With the global model, then some wise wizard can sit up there and decide, how to allocate things. But the problem is that sometimes the wise wizards don't know everything that needs to be done. And so it ends up leading to a situation where the people who are kind of out at the edges of the hierarchy get frustrated because they can't get their work done effectively. It's kind of like the difference between a totalitarian or fascist form of government or economy where you have a central planning group that decides who gets what, versus a more, democratic, more capitalistic model where each group is responsible for their own profit and loss. And of course, there's all kinds of pros and cons each way. One interesting thing to remember about the common ForkJoin pool, or the ForkJoin pool for that matter, is that there are very few knobs you can use to control its behavior. And that turns out to be intentional. And if you want to learn about why it's intentional, go watch this video by my friend Doug Lee, where he explains the rationale behind the ForkJoin pool. As you can see, there's just not that many methods here, especially knobs. You can fork, you can join, you can submit, that kind of stuff. In contrast, if you take a look at another ThreadPool mechanism that's been available for about the past 15 or so years, the ThreadPool Executor that has a lot of knobs. It's like the Swiss Army knife of concurrency models. And it's very complicated. You can control all kinds of things, but it's also, it gets a little bit unwieldy. One thing you can control in the common ForkJoin pool is the number of threads that will be in it. And we're going to talk about that in a bit. There's a couple different ways to control this. One is by setting the number of threads via a property, which is kind of limited. And another is by using something called manage blockers. This class will not go into much detail about either of those features. I'll mention them in passing briefly. But the later class, the sibling class to this in the spring, will go into more detail. You get some chance to play around with it. Okay, so that's a little overview of parallel processing in parallel streams, which uses the common ForkJoin pool.